The quantum world always holds wonders far beyond human imagination. Physicists have just discovered a completely new state of matter, quantum spin liquid. This discovery could pave the way for many new findings in the fields of fundamental and quantum physics. A group of researchers from Switzerland, France, along with theoretical physicists in Canada and the US. Researchers, including those from Rice University, believe they have uncovered evidence of a theoretical quantum phenomenon known as quantum spin liquid. This phenomenon was observed in a special material called hydrochlorhelium stannate. So, what is quantum speed liquid? Quantum spin liquid is a unique state of matter in which quantum spins. The intrinsic angular momentum of a particle is often described as the particle's own spinning motion. The particles do not arrange in a specific order, even at extremely low temperatures, close to absolute zero. Unlike the formation of a stable magnetic structure as in ordinary solids. The spins in a quantum spin liquid continuously fluctuate and interact with each other in complex ways, creating a quantum entangled state. To better understand, we need to know that in conventional magnetic materials, at low temperatures, electron spins spontaneously align in a specific order. For example, if all the spins are aligned in the same direction. Antiferromagnetism arises from the antiparallel electron spins in zinc, or the frame is created from spins in opposite directions, such as an unbalanced state. Conversely, in quantum spin liquids, the interactions between spins are extremely strong and complex, preventing them from establishing any stable order. Instead, they continuously fluctuate and become quantumly entangled with each other, forming a state of collective disorder. One of the appealing aspects of quantum speed fluid is the emergence of fractional excitations. Segment stimulation. Instead of the usual collective oscillations like those in a spider web, quantum spin liquid excitations can be regarded as quasi-particles, carry a small fraction of spin, such as a spin-in or similar quantities. These effects often do not follow classical physical laws. Proving the existence of quantum spin liquid has always been a significant challenge for the scientific community. Many hypotheses about this phenomenon were proposed very early on, but gathering convincing empirical data remains a formidable challenge. For the first time observing this phenomenon, the international research team marked a major breakthrough. The international research team designed modern experiments, such as neutron scattering and applying theoretical models to study this unique state of matter. Roman Sieb, head of research at the Polycira Institute in Switzerland, said, "Fractionalized particles have long been hypothesized to exist in quantum spin liquids. To make compelling observations in this type of material requires significant advances in experimental resolution." At the Laus-Elanderville Institute, in the town of Gros d'Eau, France, the neutron scattering experiment on a high-end specialized spectrometer yielded data with extremely high resolution. Andriy Nevdalsky, associate professor of physics and astronomy at Rice University, stated that the round scattering tool is an important instrument when analyzing the behavior of spins within a magnet. He also emphasized that this is a groundbreaking discovery, as proving the existence of quantum spin liquids had previously faced numerous obstacles. According to quantum theory, electrons have a property called spin, which makes them behave like tiny magnets. When electrons interact and their orbitals overlap, their spins can be either aligned or opposite to each other. However, in some materials like pyroglass, this interaction can be disrupted, leading to a phenomenon called magnetic failure. This is the essential foundation for the formation of quantum spin liquid. Researchers say this effect causes the electron spins to intertwine with each other, forming correlations with liquid-like properties. This phenomenon occurs when electrons interact with each other through the process of emitting and reabsorbing photons, the quantum particles of light. In quantum spin liquids, spin-ins, spin-carrying particles, interact with each other through a quantum exchange mechanism, similar to how light propagates. Nevedomsky emphasized that the interaction between spin-ins can be described similarly to how electrons exchange photons in quantum light theory. This opens up opportunities to explore novel states of matter or previously unknown special particles. The research team is now expanding their search to other related phenomena, including magnetic monopoles, a theoretical concept proposed decades ago. These discoveries not only deepen our understanding of the universe but also unlock potential applications in the field of technology. For example, quantum spin liquids could form the foundation for developing quantum computers, thanks to their ability to process complex information with extreme precision. Thanks to advancements in technology such as neutron scattering techniques and modern analytical methods, scientists are gradually uncovering how matter operates at the atomic level. In the future, research on quantum spin liquids could unlock breakthrough applications across various fields, from new material development to advanced data processing systems. Moreover, this breakthrough could pave the way for a significant leap forward in the quest to unravel the deepest mysteries of the universe. Quantum freezing environment, a promising solution to the Hawking radiation paradox and black holes. The Hawking radiation paradox is one of the most challenging problems in modern physics, posing a fundamental test for the relationship between general relativity and quantum mechanics in the study of black holes. This paradox stems from Stephen Hawking's discovery in the 1970s, when he proved that black holes are not as static as previously believed, but in fact emit a form of quantum radiation near the event horizon, later named Hawking radiation. According to this theory, a black hole will gradually evaporate and then vanish. However, the controversial issue lies in the fact that when the black hole evaporates, the information about the matter that formed it is not released back into the universe. This contradicts the fundamental principle of quantum mechanics, which states that information is never completely destroyed, thereby leading to the Hawking radiation paradox. To resolve this paradox, scientists have proposed a new model, the IC star. This is a strange quantum object, bearing similarities to a black hole but lacking a singularity of infinite density at its core. Instead, the frozen star is made of extremely dense quantum matter and does not collapse under gravity like a black hole. This difference allows the frozen star to avoid the paradoxes inherent in the classical black hole model, where the laws of physics break down in the face of infinite density. The phenomenon occurring at the black hole singularity makes the frozen star model a viable solution to the information paradox. The frozen star is not just a singular concept but also has a profound connection with string theory, one of the most pivotal theories in the study of quantum gravity. According to string theory, the fundamental particles in the universe do not exist as isolated points but are actually one-dimensional vibrating strings at the microscopic level. Frozen stars are considered a manifestation of quantum gravity phenomena, which could help us gain deeper insight into the fundamental structure of the universe. The frozen star has the unique characteristic of retaining many properties similar to a black hole, such as the ability to attract surrounding matter and analogous thermodynamic properties, but without forming singularities. This not only helps resolve the Hawking radiation problem but also opens up new research directions in understanding extreme astronomical phenomena.